Good morning or afternoon. I don't know. This is a video, so you can watch it at different times. But class is in the morning, so this is when you should be watching it for the first time. But yeah, welcome to a virtual session of Honors Geometry. And today we're going to continue working with circles. Specifically, we're going to be working with chords and circles. As a reminder, don't judge the quality of my circles. And also as a reminder, the definition of a chord is any segment for which both endpoints of the segment are on the circle. For every chord, there are two arcs that go with that chord. If the chord is not a diameter, the chord has a corresponding minor arc and a corresponding major arc. If the chord is a diameter, then the chord just has two semicircles that correspond with it. So for every chord, there are two arcs formed on the circle. If it's not a diameter, it's one major and one minor arc. If it is a diameter, it's two semicircles. Now, if you have a circle and in that circle, you have two arcs that are congruent, then the two chords that made those arcs must be congruent. Likewise, if you have two chords that are congruent, then their corresponding arcs must be congruent. So that means their corresponding minor arcs would both be congruent to each other, and likewise the corresponding major arcs would be congruent to each other. This technically is a theorem that in a circle, the corresponding arcs are congruent if and only if the corresponding chords are congruent. This is a simple proof. I guess my black marker is dead, so I will not be using my black marker. The proof is just this. We talked about last class how all the radii are congruent. I already used one tick mark, so I gotta use 3. So if the chords are congruent, you have side angle side congruence between these two triangles. Therefore, the central angles are congruent. Therefore, the two arcs would have the same measure, and since they're part of the same circle, they're congruent to each other. So that's if you have the chords were congruent, but if you have the arcs are congruent, then that means their measures would be the same, so the central angles would be the same, so you would have side angle side congruence between the two triangles. And then corresponding parts of congruent triangles would give you that the chords are congruent. So, in short, in a circle, if two chords are congruent, then their corresponding arcs are congruent. And if two arcs are congruent, then their corresponding chords are congruent. Now, if you have a circle, again, not a very good circle, and a chord on that circle, which I will just call AB, if there is a radius that is perpendicular to that chord. So if a radius is perpendicular to that chord, then it bisects the chord and it bisects the arc. So if a radius is perpendicular to a chord, then it bisects the chord and it bisects the arc. The reason this is true is because all radii are congruent. These are right angles, and that's congruent to itself. So these two right triangles, triangle AOC and BOC, would be congruent to each other by the hypotenuse leg theorem. The radii are congruent, and that segment OC is congruent to itself. Since they're congruent by the hypotenuse leg theorem, these acute angles would be congruent to each other, so the arcs would be congruent to each other. And since the triangles are congruent to each other, AC and BC would be congruent to each other because the corresponding parts of congruent triangles are congruent. So what that means is if a radius is perpendicular to a chord, then it bisects the chord and it bisects the corresponding arc. Also, I just want to say I'm not writing down these rules because you can pause this video and rewind it and then go back and listen to it again. So if you want to write it down for your notes, you have the time to do that because of the amazing technology that allows us to manipulate videos. Well, let's keep going. So, we just discussed that if a radius is perpendicular to a chord, then it bisects the chord and its arc. But if you have a chord, I've been using AB a lot. I'll use QR this time. The perpendicular bisector of that chord if you have a chord, the perpendicular bisector of that chord is going to have to pass through the center. It has to pass through the center of the circle. The reason is because of our perpendicular bisector theorem, which said that a point on the perpendicular bisector is equidistant from the endpoints of the segment. And then the converse said that if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector. Well, that center T, by definition of a circle, is equidistant from Q and R. The center has to be equidistant from the points on the circle, just by definition of a circle. Therefore, T must lie on the perpendicular bisector of QR. So anytime you have a chord, if you construct the perpendicular bisector, that is going to have to pass through the center, which means that this green line contains a diameter and it contains two radii as well. Now, if two chords are congruent, So let's say chord EF and chord GH. Clearly not to scale. Definitely looks like I drew my GH a little bit longer, but not much. And I'll call this circle X, circle X. If two chords are congruent, then they're going to be equidistant from the center. They're going to be equidistant from the center. And we know that has to be true because if we're talking about distance from a point to a line, we're talking about perpendiculars. And if we draw these radii, we know the radii are all congruent to each other. And if the chords are congruent, then triangles EFX and HGX are congruent. And one of the things we had talked about with congruent triangles is that their parts are congruent. So that means the corresponding altitude from X to side EF would be congruent to the corresponding altitude from X to side HG between the two triangles. So if two chords are congruent, they are equidistant from the center. So that's quite a bit of rules about chords that we've just gone through. So let's just recap. If two chords are congruent, then they're equidistant from the center. If a chord has a perpendicular, or on the perpendicular bisector of any chord lies the center, so the perpendicular bisector of a chord has to pass through the center. The segment that is perpendicular, the radius that is perpendicular to a chord bisects the chord and also bisects the arc. If two chords are congruent, then their corresponding arcs are congruent. And if two arcs are congruent, then their corresponding chords are congruent. So we've got all of those rules about chords. And that about does it for this video. There's going to be another video, so just keep in mind that this is not everything. Have a good day.